Finding zeros of polynomial functions. We'll be applying the Fundamental Theorem of Algebra. So what is the Fundamental Theorem of Algebra? It states that a polynomial function of degree n has exactly n roots. A root is a value of the domain that results in the function being 0. A function can have real roots and/or complex roots. A real root is an x-intercept of the graphed function. In other words, where the function intersects the x-axis. A complex root will be in the form a plus bi, where I is defined as the square root of -1. To find or verify the roots of a polynomial function, we'll set f of x equal to 0. We'll factor the polynomial and then apply the zero product property. Then we'll solve for x. So here we'll look at an example. We're asked to find all the zeros of this function. F of x equals x times the quantity x minus 6 squared. Here we can see that the degree of this polynomial function is 3, because if I multiplied everything out, it would be x to the 3rd power. So we're expecting 3 roots. First, we'll replace f of x with 0, and we'll expand that squared expression. Now we'll apply the zero product property, and we'll set each factor equal to 0. We'll solve for x, and these are our zeros. Please note that x equals 6 is a double root, and so that has a special characteristic on the graph. So here I'm going to type this function into a graphing app such as desmos.com, and here's what the graph looks like. Notice there are 3 real zeros. One of them is x equals 0, right? That's the origin. The graph crosses right through there. And then the double root at x equals 6, it almost bounces at that point. So kind of pay attention to what a double root looks like. We'll do another example. Here we can kind of get a glimpse that there's going to be some complex roots because I see that there's an I term already. The function is given to us in factored form. So we're going to replace h of t with 0. And we'll write t minus 3 times t minus 2 times t minus 3i times t plus 3i, and we'll set that equal to 0. Applying the zero product property yields these roots, or these zeros, where 2 of them are real zeros. Therefore, if I were to graph this function, I would expect 2 x-intercepts. The graph will go through x equals 2 and x equals 3 on the x-axis. So what I want to do is take the original function and I want to multiply those first 2 binomials and multiply the second 2 binomials. I want to simplify that second expression because I know that I squared equals -1. Therefore, the function can be written this way. Now, applying double distributive property, I'm going to rewrite the original function, which was given to me in factored form. Here it is in standard form. Now that it's in standard form, I can type that into Desmos or my graphing calculator, and I'll get a picture that looks like this. Now, at first glance, this kind of looks like a parabola. It's not a parabola. It is actually a polynomial of function of degree 4. There are 2 real roots, which we knew from our work earlier. We know that 2 and 3 are roots. Please notice that that is not a line of symmetry because it's not the same distance left and right of the function, just showing you that it's definitely not a parabola. There are 2 real roots. There are 2 complex roots.